Hey everybody, so today's lesson I'm going to go a little old school in our new school setting. That's what I did. Okay. Um, what I'm going to show you are a couple of demonstrations and explanations about the new words we've been learning and this new concept of how we can use things like barometers and the information I'm having you look at every day for the weather to understand what's happening in our atmosphere and what's happening around us. So first, I wanted to talk a little bit about the vocab. So for this video, you're going to want to take a little bit of notes, and there will be some times where I will stop the video. How you're going to watch this is on a program called Edpuzzle, and you will be asked questions. So it's kind of twofold. You can rewind this as many times as you want. I do encourage you to do that so you really understand, and then you'll be able to better go through and figure out what I'm trying to explain to you here. Okay, so these are the vocab words from the section of the textbook I had you read before vacation. We're going to start with this first concept of density. Most of you seem to understand that it had to do with how much stuff there was. So the best definition or most common that you're going to see is that density is expressed as a math equation. So D stands for density, and it is going to be equal to M over V, and M is mass. If you can read that, yeah, you can. Mass over volume, and that's just something really fancy way of saying you've got one structure. So this is a baseball, and baseballs are kind of heavy. They're not something that you'd want to. How many of you flinched? It's not something that you're going to want to really be playing around with unless you're wanting to actually throw and break something. But you have other devices, other types of balls. So like a tennis ball, like I could throw this and it would probably, not feel great, but it wouldn't, knock you over. And then this is, just a plastic ball, like what you'd get at like Chuck E. Cheese in their ball pit. And each of these have pretty close to the same size, which it means that they have the same volume. Okay, they have the same volume. So this is talking about volume right here. So we've defined what volume is. It's how much space something takes up. So they're as close as we're going to get in a non-science lab to things that are the same space that they're taking up. Now I already told you, so this is a baseball, okay? And I don't have a scale here, but most of you have, felt a baseball. Like this has some mass to it. It's pretty heavy, whereas this tennis ball, not nearly as massive. It's much lighter. And then this little like plastic dude, as I drop it, it's very, very lightweight. Okay, so three things with the same-ish volume, very different masses. So then we bring it back to density. Okay, density it's expressed as mass per volume. So it means how much stuff is smushed into the space. So what's your guess? Which of these three is going to be the most dense? Take a guess. Baseball. Okay, baseball is the most dense because it has the most mass per volume. Now, which one is the least dense? The ball gave it away. It like rolled. Yes, our cute little Chuck E. Cheese ball. The least dense because it has very little mass per that type of volume. Now, why am I talking about density? When we've been, we're not talking about baseballs, we're talking about the atmosphere. Well, air is made of stuff that has mass. Like that these are made of atoms and molecules and words that you've probably heard and we'll talk way more about in 8th grade. But that's what this is made of. Same as your atmosphere. Okay, your atmosphere is made of these molecules. And if I had my fun little background with my classroom and we've got the periodic table, your atmosphere, your air, okay, air is made of mostly nitrogen and then oxygen, which is good because we need that to breathe. Then there's a whole bunch of like all these other, molecules, carbon dioxide, hey, it's a thing, water vapor from the water cycle, that's making up our air, and argon and a lot of other gases that are in very, very small quantities. But these, while they are air, they are gas, they have mass. And nitrogen has more mass than less less mass than oxygen, but they both take up a fair amount of space. So air does have density because it has mass and it takes up space. Okay, follow me so far? Good. When we're talking about air density, you need to be able to kind of imagine this in your head of these molecules of air taking up space. So let's put them in some space. Okay, so say we've got a box here, and we've got another box. I'm trying to make it about the same size. Okay, boxes of equal size. So again, we've got the same volume. Now we're going to see if we can put different masses in there. So I'm just going to draw a whole bunch of different circles here, and they are going to represent our air molecules, okay? Because, as most of you have probably found, air is, kind of hard to capture in a box. So any box that we put, it's just kind of like not exactly a box of air. So this box of air, these are air molecules. Let's count them. Okay, we got 1, 2, 3, 4, 5, 6, 7, 8. We have 8 molecules of air in this box. Now let's count this one. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have 9 molecules of air in this box. So looking at these 2 boxes of air, which is going to be more dense? Top or bottom? More dense. Yeah, okay. This bottom is more dense because it has more mass in that space, more mass per volume, okay? You can also play around with your density if you're shifting the volume, but what I really want you to focus on for this is really seeing that if you've got more stuff packed into a space, more dense, okay? It's going to be driving a lot of what we talk about for the weather is the air density, because then it actually links in with these things called pressure, okay? So most of you understood pressure. It's a force, okay? If something's pushing on you, pushing up, down, any type of way, force. Air pressure, it is just literally the air pushing around on us, okay? And it's all over. It pushes on us every single direction. It pushes top, side, bottom, okay? Everywhere around the air. And it's kind of like air is, air moves around and it's a little spazzy, it's a little spazzy, okay? And it doesn't always just go in like one direction, like the band. Goes everywhere. So that's why your air pressure is coming from all sides. Okay, from all sides. And this is why, even though, as your book talked about, the amount of air coming down from the atmosphere, and yeah, you can't really see that, but from all sides, okay, air pressure all around. Your book said the atmosphere was the same amount of pressure or weight, mass, as what? It was something big. Yeah, a school bus, okay? The book told you that the amount of pressure being put down on you is the same as a school bus. Why are we not dead? It's because of that pressure from all sides. Okay, that amount of pressure, even though it's like a school bus being pushed down on you, it's also a school bus being pushed this way and that way and being, lifted away from you. So it's like equal on all sides. So it's not actually a school bus all in the one direction. Okay, so with density and pressure, we're kind of seeing where this is connecting with regards to air. Now for the fun experiment, because I had you all working with a cup that had water in it. And I saw a lot of your pictures. Some of you are more successful than others. Okay, I think one of the key things that some of you may not have had was a piece of cardboard that was bigger than the mouth of your cup. And one other key part of it that does seem to make a difference is the fact that if your cardboard has a little bit of a slip, so this is literally a facial tissue box that I tore apart, if it has a little bit of a shine to it, or even just something like a note card, it does really, really well. Another trick is that you want your cup to be almost all the way full, and that's an important one that I'll show you here in a second, okay? So just to make sure I don't make a mess in my basement, I do have a bowl here. I'm going to do this over because, I don't really want to clean up a mess. All right, so you position the card here, and you turn it over, okay? No slips, no spills. And let's see. Boo! And I think it was because my card was bent a little bit. So that was try number one. Let's see if I can get it on try number two here, because I really want to show you why this works. Okay. If you don't succeed, try again. Here we go. All right, so second one here. I'll get a little closer so if it does fall. Nope. Okay, it is not working for me tonight. I think it has to do with the fact that I'm trying to do this at a late hour. This was not done this morning. No, it was done late last night. Okay, third time is the charm. I'm hoping. Okay, so I'm actually going to do something radical here. See if this makes a difference. Okay, so I got it here. Okay, so the reason why I think it's working now with this one has to do with two things. The amount of air that's trapped inside, also the size and the bend of the card. Because this is not just an air pressure trick. This is an air pressure and a thing called surface tension. So the fun thing like that the water can do with the meniscus and everything. So the air pressure, okay, that's inside this glass, okay, there's actually less air that we've trapped in here. So like the 8 molecules than there is on the air that's all around us. And because air pressure comes at us from all sides, there's actually more air pressure just randomly pushing up on this card than there is actually inside here. So the weight of the water is really not the issue here. It has to do with the air pressure inside versus the air pressure all around. So now this is the question. What is actually causing this card to stay up? Okay, remember it's that air pressure inside is less than the air pressure on the outside. Okay, third time. Okay, so hopefully some of you stuck with it enough to really make it a go. All right, so that's my fun little project. So we've now, in however long this video is going on, we've covered half of our words, and I think we've gotten hopefully a little bit better understanding of these concepts, because I know they're really hard to just read and learn on your own. Okay, I understand that. That's why the fun video with all my gadgets. Okay, now we're on to barometer, which you've watched a couple of videos about, and I've shown you mine, and the discussion of the difference between the mercury and the aneroid barometer. Okay, so first we're just going to talk about barometers in general. Okay, so I'm going to bring over here my versions of the at-home barometer that I made, that I've been actually kind of disappointed with, that it has not worked really all that well at all. So I took these in from outside. They had been outside for the entire week and then some, and like right now it's not even showing that like these have not moved, like literally not moved at all. So if you've had your DIY barometer at home and you're like, it's not doing anything, Ms. McLaughlin, don't worry, mine isn't either. Okay, these have been kind of duds, and I have some theories as to, or some hypotheses why, and I'll get to that in just a second. But again, if your barometer at home is not working out really well, don't worry, we're in the same boat. Okay, so I'm going to come back to that in just a second. I did want to show you my fancy dancy hurricane glass barometer, which is similar to, but kind of almost opposite of, a mercury barometer. This hurricane glass and the mercury barometer, they both work off of that concept of the air pressure inside of the vacuum versus the air pressure all around. Okay, the difference being, in the mercury barometer, if you have high pressure, the mercury actually goes up higher. And when you have low pressure, the mercury in the mercury barometer will actually go lower. My little hurricane glass is the opposite, and this is why. In high pressure, this actually will force the water, because the air pressure surrounding is acting on this liquid that's here in the arm. Okay, this is a vacuum. When I filled this, I had to have it upside down. If I put it upside down, it'll totally mess it up. But I had to fill this upside down so that I created a vacuum, like a pocket of air in here. And when I flipped it up right side up, this air is what is being acted on to expand and contract. And so the air pressure around the outside, it's causing this column of the water to go down or up, depending upon what the air pressure is around it. So for right now, we actually have high, medium pressure. And what's really interesting, I should take a picture of it before I brought it downstairs. It's colder in my basement than up in my house. And temperature is something that really, really impacts air pressure, because it impacts your density. And I'll come back to that. But the pressure right now here is actually medium high. Okay, if it was low pressure, that water would be up here or even starting to fill this space. When we have really, really high pressure, it's going to go all the way down here almost to the bottom. Okay, so that's why I say this is like medium-ish pressure, because high pressure is going to be pushing it down. High pressure is heavy, dense. It's really, really putting a lot of force, and it will ultimately push that water down. Low pressure, it's like, you can expand, no big deal. And it's going to bring that water, it'll let it come up because there's not going to be much pressure on it. Okay, so what part of this tube will the water be in? Where will the water be in this tube at high pressure? Towards the bottom or towards the top? Okay, you got your answer? All right, where is the water going to be if there's really low air pressure? Will it be down towards the bottom or up towards the top? Got your answer? Okay. For a high pressure, okay, high pressure, it's pushing down on the water, so the water is going to be squished and we'll have high pressure. Low pressure, it's all relaxed and the water can like float back up because it's chill. And so the low pressure, this water will be up towards the top. Okay. So that's similar to our mercury barometer that was described in the textbook, and that the video, the extra video I think I said you could watch for fun, talked all about the mercury barometer. But it has to do entirely with your air pressure literally pushing on these liquids, and they're going to respond because of that pressure. Okay. Now this one here is similar to, and I've taken pictures and kind of put this on, this is similar to the aneroid barometer. There is on the back here, you can kind of see there are some coiled metal in here, and it is under, it's in a chamber, and depending upon the pressure, the air pressure, the coil will expand or contract, which is attached to this needle, and the needle will move back and forth. So again, as it showed, this is what I use to show the accuracy between the two of these here. Okay, so we've got kind of medium-ish high pressure, same as what I'm saying where this is medium-ish pressure. Okay, so there is some connection between our devices. And this is showing in a unit called HPA, which is hectopascals. So there are so many different units with measuring barometer. And the mercury barometer is like, well, it's not the gold standard because, it's the mercury standard. Gold, okay, it's a little chemistry humor. Okay, so this barometer, though, it is showing, and I've seen it kind of swing back and forth. So this is a much more sensitive and accurate barometer than even the hurricane blast barometer, and most definitely better than my barometers here. Okay, so now I'm going to kind of circle back around and we're going to talk about this density and why I'm thinking my little DIY barometers aren't working. So I made these barometers inside my house. It was a nice toasty, like 72, 69, 67, 60 or 70 degrees. And no time has the outside been even close to that temperature. And from a density and air pressure standpoint, if you've got warm air, okay, like these molecules are speeding around and they're actually really spread out because they are flying all over the place because they're so hot. Warmth and density and pressure. Temperature, density, and pressure are all interrelated when you're talking about air because the molecules are so easy. They're air. I mean, they're like poof. You can heat them up and cool them down, and they're very, very reactive. So the reason my barometers haven't really been all that responsive is that they were at such a high temperature to begin with that all they've done is shrunk down, and there wasn't actually enough air molecules in here to really show any kind of change. So what I'm going to do in the next day or so is redo these outside when it's kind of cold and let them kind of like capture enough air molecules inside such that when it does actually fluctuate with the temperature outside, I'm hoping I start to see this go up and down. Because what's going to happen is as the air molecules that are trapped inside my device here warm up and there's less air pressure pushing down on them because all those other molecules are speeding around and they're not pushing as much, this will expand and it will puff up the saran wrap, which then will make the other way, this way, that will make the needle go down. so that you actually have low pressure. So your barometer device like here, it's going to show your high and low pressure in kind of like the more normal way that we're thinking about. And when it gets really cold and the air pressure is heavier and pushing down, okay, it's going to force, see I can do it, it's going to force this needle up because that pressure is pushing down and it's all kind of shrunk in. But it all, again, the reason why I think my barometer didn't work is, yeah, it's because I did it inside and there weren't enough air molecules in here to get it to effectively expand or contract. Okay, we're coming into the home stretch here. Altitude. I know I didn't really have you read about it, but it is important to link this with your density and your pressure, okay? So if you've got kind of like a mountain, okay, this is my mountain, you know, there's my snow, and here's my little mountain climber, okay? I got their little hat on, okay? So that's my mountain climber. This is my mountain. So we got sea level down here, and the reason I'm talking about altitude right now is because your next piece of information that you're going to read about for next time is going to be talking about our atmosphere. Okay? Because the atmosphere is where we really define what this air is doing all around us. And if you're going from Narragansett Beach, sea level, up, you know, you go into Vermont, New Hampshire, you want to go to Bretton Woods, you want to go skiing, you're now, you know, like a healthy little tick above where you started. And you're getting literally closer to outer space. And there's less of these air molecules that are ultimately pushing down on you and even pushing on around you. They're all spread out. It's colder up here, and it's linked to your density, which means your pressure. So altitude is linked with these two concepts, okay? Because the few things that I said that are linked, density, temperature, and air pressure. I really wish I had a better board, but I don't, okay? So what are these three things that are linked? It's really hard for you to see. Okay, I have temperature. Oh, that's horrible. Push it there a little bit. Yeah, that's stinky. Ha, I'll put it here. Okay. Okay, these are all linked. Okay, as your temperature increases or decreases, it will cause your air pressure to also increase or decrease, and likewise your density increases and decreases. Really, it's kind of temperature impacts density, which impacts air pressure. Okay, so what are they? In what order? Yeah, temperature is going to impact the density, which impacts your air pressure. Okay, all right, so that's all I got for this lesson today. You are going to then read in your textbook. Look at that, I'm kind of prepared. The next section, you're going to be reading pages 522 through 527. Okay, so 522 to 527. I will post that in Google Classroom because it's going to be a nightmare to read there. Okay, and then you'll be doing the questions that I have listed in Google Classroom because you're going to be introducing yourself to this next concept of atmosphere and these different layers. Okay, so this is all connected with atmosphere. Okay, density is how we describe what the air kind of how squishy it is. Like, is it all smushed all together or is it kind of all relaxed? And we talk about, like, we can measure this density with the pressure. And the pressure, we use these tools, okay, barometers, and there's two kinds of them. And then altitude comes into play when you're going up into higher levels of the atmosphere, okay? So you have your notes from the words, you have your homework, and hope you enjoyed my basement science. Okay, I gotta stop this now. Bye.